Good morning, everyone. The title of my presentation is Answering Skyline Queries over Incomplete Data with Crowdsourcing. My presentation is divided into 6 parts. First, I introduce the background of our work briefly. Then I describe the framework of our proposed BayesCrowd. Next, I present the details of BayesCrowd framework in the modeling phase and crowdsourcing phase. Finally, I demonstrate the experiments and conclude our BayesCrowd. First of all, the Skyline query retrieves the objects which are not dominated by any other object in the dataset. This query has a large application base in many real-life scenarios, such as decision-making, profile-based recommendation, location-based services, and so on. On the other hand, incomplete data is universal in many real-life applications, including data integration, the limitation of devices, system failure, privacy preservation, and so on. As well known, the machine has limitations in some cases where the human is powerful. Towards this, we resort to crowdsourcing techniques to harness human intelligence for Skyline queries over incomplete data. Here is an example of Skyline query on incomplete data. It is a toy dataset from moving recommendation system. Each object is a movie and each attribute is a rating from one audience. There are 5 movies with ratings from 5 audiences, A1 to A5. The values of O1 and O4 are certain, but the missing values in O2, O3, O5 are not determined. Thus, the Skyline query results cannot be obtained. As a result, we propose a novel crowd-Skyline framework BayesCrowd, which handles the Skyline queries over incomplete data via crowdsourcing. There are 2 phases including modeling and crowdsourcing in BayesCrowd, and we develop methods for modeling and crowdsourcing. We model the relationship in data and represent data efficiently. Then, based on the modeling, we present probability computation methods and task selection strategy to support crowdsourcing. Extensive experiments demonstrate the effectiveness of BayesCrowd. Let me introduce the framework of BayesCrowd. The figure in this slide plots the framework of our proposed BayesCrowd. BayesCrowd is invoked when received an incomplete dataset and a query. Specifically, BayesCrowd contains 2 phases, the modeling phase and the crowdsourcing phase. BayesCrowd first trains the Bayesian network over the dataset to learn probability distributions of missing values. In the modeling phase, the condition of each object being a query answer is generated using the C-table model. When entering the crowdsourcing phase, BayesCrowd takes into account users' requirements and selects text for crowdsourcing, which involves a critical component, the probability computation. Then the chosen texts are posted to the crowdsourcing platform. The answers will be later returned by crowd workers. Finally, BayesCrowd outputs the query result set while updating the C-table. Now I describe the details in the modeling phase. We show the details of C-table construction in modeling phase. First, the dominator set contains all objects that may dominate an object O. We can derive the dominator set on the sample movie dataset as the figure shows. When the dominator set is obtained, we start to construct the C-table. In particular, the condition of an object is the condition of an object to be a Skyline point. We develop a getCtable algorithm to get C-table, which uses a threshold parameter alpha. If the dominator set size of an object is larger than the product of alpha and the dataset size, we set this object's condition to be false. This means that the object is considered impossible to be a Skyline point. As the figure below depicts, O2 and O3 are certain Skyline points, as there is no object in their dominator set. As for other objects, only when all expressions in the condition are satisfied, the object belongs to the query result. I will introduce how the crowdsourcing phase works in this section. In the crowdsourcing phase, there are two main steps, including probability computation and crowd task selection. In the first place, we need to compute the probability of the condition of an object. The intuitive solution, called naive, to compute it is to evaluate all the variable value combinations of the variables, which is at least as hard as the sharp set problem. Meanwhile, abbreviation of Davis-Putnam Loggeman-Loveland search is a popular and efficient solver for the sharp set problem. As a result, we propose an adaptive DPLL algorithm for probability computation. A DPLL recursively selects the most frequent variable in a condition and breaks the conjunct correlation in the condition as quickly as possible. Considering budget and latency constraint, we select crowd tasks in each iteration through two steps. At the first step, we employ Shannon entropy as a metric to quantify the uncertainty of objects, as the formula shows. PO in the formula is the probability that the object's O's condition holds, which is calculated in the probability computation. We choose top K objects with high possibilities to be query answers. In the second step, we select expression among the condition of the previous chosen objects. Specifically, we develop three strategies. The frequency-based strategy selects the most frequent expression as a crowd task. In contrast, the utility-based strategy introduces a marginal utility function to measure the benefit of crowdsourcing one task. Particularly, the information gain is utilized to measure the expected quality improvement of choosing an expression E of object O. In addition, the hybrid heuristic strategy combines the advantages of FBS and UBS. HHS introduces a parameter M to enable a heuristic in order to control the computation cost. Here I present a comprehensive experimental evaluation to study the performance of BayesCrowd. In our experiments, we utilize two datasets including NBA and synthetic. NBA is a real dataset containing 10,000 records of player competition information from 1979 to 2004. We use 11 attributes including total points, total rebounds, and so on. In addition, for scalability evaluation, we generate the synthetic dataset with 100,000 records and 9 attributes. 2 attributes are said to be missing in NBA, while the missing values in synthetic are random. Meanwhile, the simulation settings of crowdsourcing are reported. We set the worker accuracy to be 1 and choose majority voting to get task answers. Please note that each task is assigned to 3 workers. We employ the CPU time and F1 score as a metrics of efficiency and accuracy, and the experiments are reported as follows. The performance of our algorithms, comparison with state-of-the-art method CrowdSky, and the effect of parameters. We verify the performance of the following algorithms in our experiments. GetCtable algorithm for C-table construction and ADPLL algorithm for probability computation. The baseline algorithm is compared to GetCtable, which obtains the dominator set and C-table strictly. It is obvious that GetCtable is faster than baseline under different missing rate settings. Meanwhile, the naive method to solve the sharp set problem without acceleration is worse than ADPLL all the time. It is easy to find that higher missing rate makes the query harder, thus increases time cost. We compare BayesCrowd with the state-of-the-art CrowdSky. One can find that BayesCrowd is better than CrowdSky in terms of tasks, runs, and time. The less tasks and runs demonstrate that BayesCrowd needs less monetary cost and latency. The less time cost means that BayesCrowd is of good scalability. In addition, the cost of both BayesCrowd and CrowdSky increases with the growth of data cardinality as the dataset becomes larger. These figures show the corresponding experimental results when varying the amount of budget. BayesCrowd FBS is the fastest and achieves lowest accuracy. Meanwhile, BayesCrowd UBS needs highest time cost but achieves highest accuracy, as it selects the most helpful tasks all the time. BayesCrowd HHS balances efficiency and accuracy and performs between FBS and UBS. It is also obvious that the accuracy climbs up gradually with larger budget, while the efficiency drops. Compared with BayesCrowd FBS or UBS, we show the corresponding experimental results when varying M. For BayesCrowd HHS, its accuracy gets higher with the growth of M. In other words, it performs more like BayesCrowd UBS and is able to get same performance as BayesCrowd UBS when M is large enough. We report the corresponding experimental results on both datasets, varying the threshold value alpha from 0.001 to 0.01. When alpha is large, the more objects are considered to be a result, thus efficiency decreases but accuracy increases. But when alpha exceeds 0.003, the performance improvement is not obvious as the new considered objects are not truly results. We changed the worker accuracy from 0.7 to 1. We found that time cost is not sensitive to worker accuracy, and higher worker accuracy makes query results better. It's obvious that the accuracy of BayesCrowd UBS and HHS grows faster than BayesCrowd FBS. We conclude the presentation. To summarize, we propose a novel cross-Skyline query framework, BayesCrowd, and develop methods to implement it. Specifically, we present an effective approach for suitable construction and an efficient algorithm to accelerate the probability computation. We also propose a suite of task selection strategies. Extensive experiments show the superiority of BayesCrowd, which can achieve higher accuracy with less cost. Thanks for your listening, and if you have any question, please contact me.